Right, so welcome Maurice Rojas from the National Science Foundation and Texas A&M. So he'll speak on Fewnomial hypersurfaces and their connected components.
Yes, thank you very much, Alexei. So again, apologies for the delay. So I'm going to talk about a few things today. But first off, I would say the main trick for today, and of course I'll give an introduction, is essentially piercing walls of discriminant varieties. So the idea is that discriminant varieties are very classical, and if you look at the space of all polynomials, the discriminant variety is somehow this subset of bad polynomials who have zero such which behave a little bit differently, and as you go into different components of the complement, different topological behavior appears. And there's a lot of quantitative questions that we don't understand yet, and so to get new bounds, and I'll give you new bounds, all you have to do is just pay more attention to how you cross over these discriminant boundaries and what happens. So that's the primary trick. So I want to give a little bit of background. And the first bit of background I'll give is this. I wanted to go to 1609. No later than that, we'll look at Descartes. And Descartes said that essentially a polynomial of this form has no more than 2 minus 1 positive roots. And it's independent of the exponents. And I'm going to assume the exponents are going between 0 and here. And you have to assume, of course, this CI isn't real. Okay. Now, he stated the result he actually didn't prove it, but it's worth noting that the theorem was proved using Rolle's theorem. This was proved eventually via Rolle's theorem. And this is hinting at something which allows you to generalize farther. So the key trick behind these quantitative results involving sparse polynomials seems to be looking at the right differential operator, or at the right kind of theorem involving differential operators. All right, so moving forward a little bit more.
How did Descartes think about it?
I'm not sure. That's a good question. I have a friend who collects a lot of proofs of Descartes' theorem, so there's maybe about 20 proofs at least. He might have been thinking about it more algebraically. So actually there's a really neat proof you can do by using kind of a modification of Vandermonde matrices. So if you look at certain determinants and do some trickery, then you can get it that way too. There's entirely algebraic proofs too. Rolle's theorem, I think, my history isn't so good, but it came out around the same time as Descartes' theorem, and I can't remember which one came first.
Before calculus.
Yeah, I think so. I forget which one came first. Maybe it was in the air. I don't recall. But what I want to do is go to higher dimensions. So now around 1980 or so, Zelevinsky proved. I mean, it's I'm not completely up to date on Sebastianov's role, but he was very important in the foundational work. Eventually, the theorem was proved, and I think was stated in a paper of Kovansky's, and it certainly appears in his book, 1991. But he did the following. If you look at a system of equations of the following form, so let's take a look at something like sum of Cij x to the aj. Let's say j equals 1 to t. And let's do it this way. And do it this way. J equals 1 to t. C and k x to the j, like this. And this is where you assume that A1 through A and AT, these are now vectors. You can allow them to be real. And when I say x to the aj, I mean to use multi-index notation. So you're going to do this, like that. And the CIJs are going to be real. Okay, so if you look at a system of equations like this system of equations, which we'll call F, okay, this guy has no more than a certain number of roots. The positive worth it. This guy has no more. Something on this order. So the O of n plus k, I'm sorry, t plus n, I'll be careful here, should be like t squared. Non-degenerate roots. In positive order. Okay, so this bound is completely independent of the degree, but it's a very, very large bound. And I am being a bit sloppy here on purpose, so I don't want to get into the too much in detail about this bound. But this one was also proved via Rolle's theorem, generalization. Also proved via the Rolle theorem. And again, question?
Yes, sir. What's the meaning of non-degenerate?
Non-degenerate, so what do I mean by non-degenerate? Thank you. Glad you asked. I mean the Jacobian of f evaluated at a particular root is non-singular. So you look at this matrix of partial derivatives. I guess if you could let this guy be f1 through fn, you know, f1, etc. through fn, then you look at these partial derivatives. That matrix evaluated at a root.
Yeah. So that also takes care of like repeated equations, right? So like if you have a system like that's.
You're right. You're right. Yeah. You're right. So when you have a system of repeated equations, then all the roots are degenerate, and then this theorem says nothing. Mm-hmm. Okay, but you can use this theorem to give information about the more general case. Mm-hmm. So let me get to that. So here's what happens. So note, here's some older tricks.
Well, there's some general easy to state theorems about when this satisfies the transformability hypothesis. So a generic case has finitely many.
We'll get to very precise theorems of that nature in a minute. That's where the discriminant variety comes in. So basically, the discriminant variety, if you're away from the discriminant variety, then this bound holds. And I actually will give a pretty precise definition of the discriminant variety in a bit. So, yeah, thank you for asking. So it turns out via some older tricks, you can also prove a similar bound for a number of kinetic components. Of the real zero set, I'm going to kind of switch gears here. Somebody of this shape. So now I'm going to kind of switch notation a bit. So E1 dot Y1, oops, dot Y plus dot this CT C A T dot Y, this guy. Okay, so let's be careful with the notation here. I switched from one polynomial, one variable sparse, meaning that I have t terms, to an n by n system, which is in some sense sparse. I'm controlling how many monomial terms are allowed to appear. Notice that every equation potentially has the same monomial terms with different coefficients. And I'm sort of switching over notation to exponential sums. Okay, so this should not confuse you. So Descartes thought about integer exponents it turns out if you prove things by Rolle's theorem, there's no problem allowing real exponents. By the way, if you're on the positive numbers, real exponents are okay. If you take negative powers to real powers, negative numbers to real powers, then you start getting into trouble. Likewise over here, it's perfectly okay to take real exponents. That's perfectly fine and well-defined. Here, I'm switching gears slightly, but it's pretty clear. If I have a multivariate polynomial and I substitute exponentials, then I can very easily get an exponential sum of this form. So my point is that exponential sums are a slightly more general setting, and they're also a more comfortable setting. Okay, so henceforth, I'm going to be talking about exponential sums. So here, there are no assumptions. No assumptions on singularities.
Let me see if I can understand. That's a dot product of the vector.
Yes, that's a dot product. Yes, that's a dot product of vectors. It's a dot product of vectors. So in other words, I have y equal to y1 through yn. So this is, in some sense, it's morally a hypersurface. Okay. All right. So you can get similar bounds. I'm not going to get into the exact shape of the bounds because I'm going to give you more precise bounds in a particular setting. So now let me finally give you what the main theorem is. So the main theorem makes some assumptions, but you get bounds that are way better than possible before. So I want to say this correctly. So the main theorem is the following. And this is joint with Mounir Nisse. Sorry, go in alphabetical order. Against Forsgard. And Nisse. And myself. And it goes as follows. If the real zero set is smooth, this guy, then it has no more than a certain number of components, less than equal to, and I'm going to state this carefully. I want to switch over to n plus k dot 1 for technical reasons. So t equals n plus k. So we'll still see why I do things this way. I'm assuming the number of monomial terms is n plus something, some positive quantity. This is a very, very mild technical condition. It's really actually very, very natural. I'll explain this in a minute. But number of connected components is as much. It will be on the order of the following. I want to say this carefully. I'll say this will go then. This 2 to the k squared, and here we have n plus 2, something of this nature. Maybe around this much.
Should I be thinking of this as the a's are fixed and the c's are variables?
You can think of it that way. I mean, this is independent of the AIs. So, no matter what choice of AIs you have, number of connected components, you can vary the CIs. You're never going to have more than that many connected components. So once you fixed everything, you never have that many connected components.
In order, say, to see that the hypersurface is smooth, I could just perturb the c's, because you have enough exponential terms.
That's a good question. You could just perturb, and you could do a little more trickery to handle the degenerate case, but I don't want to talk about the degenerate case right now. I want to keep things simple for now. Probably a similar bound is possible. But the point is, here's the interesting part about the bound. The number of terms is n plus k, n plus a little bit more. So if this little bit more is constant, then what you wind up getting is a bound which is polynomial in n, which is kind of nice. And this is not true of any previous bound. So there are previous bounds in the sparse setting, which would not have gotten this. Yeah. So I want to pause for a second and say something about motivation. So why should we care about this? So why should we care? Okay. Well, I mean, there's the simple answer is like, okay, it's a hard problem, and it's a very basic quantitative question that it seems rather hard, and it's been around for some decades. But here's an interesting motivation. So one motivation comes from complexity, actually. It's actually one of my favorite motivations. So consider an algebraic circuit of this kind. Like this. So what I'm going to draw a graph, and the inputs of this graph are going to be variables to high powers, and the output is going to be the value of a polynomial. That's what I mean by an algebraic circuit. It's a directed graph where the inputs are variables or numbers, and out comes a polynomial. That's all that I mean. So you can imagine something of this nature. So I'll just put a couple of notes here. So for instance, I could have x1 to the 9th, maybe minus 7. Here I have x1 to the 100, and here I have 3. Here I have x1 to the 47, and here I have minus 1, and I have x1 to the 10th, and here I have plus 10. Okay. And now what I'm going to do is add these guys together. Then I'm going to multiply. And then I'm going to add these guys together. Okay. So if you just imagine this for a second, if you think about it for a moment, all this circuit is doing is representing a polynomial of a certain form. And what this spits out for you is the polynomial. Well, polynomial is a sum of products of sparse polynomials. So here what you get is, for this little example, is x1 to the 9th minus 7 times x1 to the 100 plus 3 plus x1 to the 47 minus 21 times x1 to the 10th plus 10. Okay. So, my point is that you can represent polynomials in this strange way, but the deeper question is how efficiently can you represent polynomials of all kinds? So here's what I'm getting at. In complexity theory, one big goal is to rigorously prove that certain hard problems, certain hard decision questions, certain hard decision problems cannot be solved by small circuits, Boolean circuits. So I'm not going to review too much complexity theory, but I just want to say that this is a major portion of a part of complexity theory. And it's an extremely hard problem. It's a problem which has been around decades. I mean, it's very rare that you can actually take a problem and actually prove that it is hard, not doable by certain computational models. And what's interesting is that there's a connection between the roots of sparse polynomials and structured polynomials and classical complexity theory. So here's the really beautiful connection. And this is due to Quadrant. Kapranov from around 2011, 2012, I forget exactly. And so it goes as follows. So I'm going to state it in a very strange way first, and then I'll give you the precise statement. And I hope by stating it in a strange way first, it's a little bit more intuitive. I'll say it this way. If there are no small but mighty polynomials, then the permanent is hard to compute. Okay, this is a very, very rough and vague statement, but it's meant to give you a little bit of intuition. But I'm going to restate this in a more precise way. So, more precisely, here's what you should say. If any polynomial of the form, all polynomials of the form this I equals 1 to k, product of k equals 1 to m, fij. Fij being the polynomial integer coefficients, one variable, at most t terms. So any polynomial of this form, let's see, has no more than this many roots, k plus m plus t, of 1, so some absolute constant, roots in z. Then the permanent permanence of n by n matrices cannot be computed by circuits, constant free circuits of size, polynomial n. Okay, so this is, it is not proven that VP is not equal to VNP, but it is akin to this. Okay, so again, without digressing too much, it is a major question whether you can compute permanence by families of circuits of small size. Notice that the circuit that I wrote here a few minutes ago was of a very particular form. It was depth 3, and you put in high-powered inputs. But you can imagine more general circuits. You can consider arbitrary circuits of arbitrary depth. And so that's more what the VP versus VNP conjecture is about, looking at arbitrary circuits. So it's kind of amazing that you can say something about arbitrary circuits by looking at a very, very restricted class. So that was one of Korben's discoveries. And what does it have to do with sparse polynomials? Observe that in some sense, a t-nomial, a polynomial with just t terms, is sort of a special case of something which is SPS. SPS meaning, sorry, this is strange. Yeah. Sorry. This is a sum of product of sparse, sum of product of sparse. Okay. This is an arbitrary algebraic circuit. Okay. So my point is that I started talking about sparse polynomials. There's a slightly more general class of polynomials, or this is how I'm more efficient in encoding. You take a sum of products of sparse polynomials, and you see these guys, they need to be sparse. They're somehow a more general class. So you can more efficiently encode arbitrary polynomials in terms of these guys. And then, of course, there's arbitrary polynomials. And so this is sort of this slightly more general and more general family of polynomials. And by looking at multivariate systems actually give you a little bit of insight into these kinds of these polynomials. So that's something to observe. So here's the key thing, looking at multivariate polynomials. systems helps you with insight. SPS. I'm not saying this is the way you're going to solve this hypothesis, but I'm saying that it will at least be able to get a little bit of insight. So that is one potential motivation. All right.
What is SPS again?
SPS, sum of product of sparse. Sum of product of sparse.
Sum
Of products of sparse polynomials. That's what I mean by SPS. All right. So now I want to start talking a little bit about discriminants. Mike, you have a question?
Koren prove some bound on the number of integer roots of these systems if they're integer bound?
Well, that's a really, really good question. So I should observe this, that we have a little bit of evidence. We have a little evidence towards the hypothesis of Koren's conjecture. It's still rather open. And so, yeah, he made this, the bounds that we have are still exponential in some of the parameters. That's the problem. And so, I don't want to digress too much. Also, I don't remember off the top of my head exactly what the bounds are, but unfortunately, the best bounds that we have are still exponential in one or more of these parameters. We're still not there. We're still rather far. I should also mention that there's weakenings of the hypothesis. So it gets more technical, but actually, you don't even have to be polynomial. You could actually have weakly exponential bounds and still be able to say something. So it's a really interesting line of attack. And it's still very, very hard. I mean, we're waiting for more advances, but it's one that's worth looking at. Okay.
The Chebyshev polynomials have 2 to the k zeros, right?
Yes, but
And they're easy to produce by some, and they're all 2x squared plus 1 or something.
but it's recursive. That's recursive. And the thing is, yeah, SPS is strictly non-recursive. That's the thing. Yeah. So that's a good observation.
Uh-huh.
So this is something which sort of escapes that trick. So yeah, this is. I should also mention that this is, in some sense, a refinement of earlier work of Mike and Steve. So Mike and Steve had this very famous Tau conjecture. This conjecture having to do with polynomials represented in a still more efficient way. Actually, you could do this. You could do SLP. You can sort of put straight line programming here. And so what Korben did is that he sort of looked at a slightly simpler class of polynomials. So he basically sort of weakened, your hypothesis, it's really a beautiful problem. And we have no idea how to solve it. And so he sort of found an easier problem, which you still don't know how to solve. Okay, but that's where we are. Okay. So now, here's the question. What is a discriminant and where do they fit in here? And why should they matter? So if we're going to understand these quantitative questions, we should look at some specific examples. So let's look at some concrete systems. Quantitative estimates. And where discriminants occur. Because that's going to be the main technical tool. The way we get these better bounds, the way we got the main theorem, is by looking at discriminants somehow. So here's a puzzle. So this is a very concrete puzzle. Look at polynomial systems of the following form. Let's look at 1 plus, let's say alpha x to the a, y to b, plus beta x to the c, y to d, plus, let's say, gamma x to the e, y to the f. I'm just throwing out random letters here. X to the g, y to the a. Look at this guy. So here's a polynomial system. I'll call him g. G1, I have to give him a different name. Call him N or something. Call him big M. So here's a polynomial system. 2 equations, 2 unknowns, 3 terms each. And the question is, what's the maximal number of roots in the positive quadrant we'll have for this guy?
Can you say that again? I'm sorry.
The maximal number of roots in the positive quadrant.
Uh-huh.
So what is the maximal number of isolated roots for the system M in R2 plus? So what could that be? And so, okay, I just gave you some theorems, and I gave you these theorems in a rather sloppy way, but I'll give you concrete bounds. So Khovansky's bound from 1980, if you apply it in the best possible way, it would tell you that the number of roots of such a system, I mean, theoretically it's finite, no matter what, it would give you this, 5,184. Okay? So that's what the numbers come down to. And it's rather large. Okay? That's if you sort of change variables and do various things. Now, a bit later, I was joined with some friends. We got in a little horse race, and we managed to get this down to 5 as tight. So there actually are systems that give you 5 roots. So what is the puzzle? Well, the puzzle actually is something else. So what is the puzzle? The puzzle is to actually give a system like that. Can you find a system? Can you find such a system? So 2 equations, 2 unknowns, 3 terms each. Can you do that? So this is where discriminants come in. Because if you try looking for these guys, it's not easy. Not actually that easy. So let's start looking at this like maybe an algebraic geometer might want to look at it. So one approach would be the following. So here's a simple approach. And this will build into something a little bit bigger. So I'll change things around a bit. Let's look at this. Let's look at something of a slightly different form. Let's look at something like on x to the d plus alpha times y to the d over 2. So let's d even. I'm going to look at a particular kind of polynomial, minus y. And I'm going to look at y to the d, beta x to the d over 2 minus x. Okay. Why did I do that? Historical reasons. So I'm limiting it further. Okay, so I'm looking at this very, very special class of equations. And the question is, for which alpha beta do you get a degenerate root? Okay, so I'm hinting at a fundamental trick here. The fundamental trick is that when you look at polynomials in one variable, polynomial in one variable has a graph. If you jiggle the coefficients, you affect the graph, and you somehow affect how many roots the polynomial might have. So what I'm going to do is look at this family of polynomials, fix d, and move around alpha and beta. And presumably, if I move around alpha and beta, and if I get an understanding of where the degenerate roots are in the coefficient space, then I know regions where the number of roots is constant. And then I'll be able to solve the problem. So that's the basic idea. And in fact, let's do more. Let's assume that alpha and beta are positive. Let's do that. So if you do that, something interesting happens. So here's the alpha beta plane. And if you look at the possible values of alpha and beta, which ones give you a degenerate root? Here's what happens. You get something like this. That. So I'm drawing a really bad picture. But it's a curve which looks like this. And here you have a constant number of roots. Constant number of roots. Real roots, or positive roots. Positive roots. and it's constant over here, constant. Okay? And if you do this experimentally, you can actually do this in the computer algebra system, you will see that this funny little curve, you hardly ever see this. And in fact, you have this really, really tiny region. This region is very small, it's very hard to see. So the key is that those with 5 roots are here. Okay? So this doesn't look very dramatic, but
So
yeah.
where is D in this picture?
D, I'm going to fix D. So that's a good question. I actually, let us just take D to be 6. Okay? I'll do that, yeah. And no, but there's, I'm skipping over a lot of suffering. So the first examples found for this one were D equals 104. And this is back around the year 2000. And in the year 2000, this shows you how computer algebra systems progress. In the year 2000, looking at the system and counting all the real roots rigorously for degree 104 was a pain. I mean, you could do it, but it was painful. It took some number of hours, I don't know, maybe under 2 days. And you really want to understand this. And so what we finally did, some students of mine and I, we got together and we took D down to 6. And we found that we could still build counterexamples like this. So what you actually get, here's an example. X to the 6 was 40 for 31sts. Y to the cube minus y. Y to the 6th plus 40 for 31sts. X cubed minus x. Okay, that's one of the simplest examples that we found. Okay. So, okay, big.
So you mean this system has got 5 roots?
Yeah, it's exactly 5 positive roots. Okay, not easy to build. And so, the explanation that we found. Okay, why is it that it's so hard to find these guys, and what is really going on? Well, the extremal examples seem to be in these little exotic chambers. Okay. So now let me get before I give you the bigger definition, let me give you another example.
Do you know the average number of real roots?
Okay. Here's where it gets interesting. So, I'm glad you mentioned that. So here's a little side note. So Mike is keeping me honest. There's things that I wanted to mention and I forgot if it wasn't for him. Let's see, there is recent work. On random, sparse, random and sparse systems, monomial systems. And so for this one, actually, I would not be able to tell you the exact number, the average number of roots for this guy. Most likely pretty small. I can actually tell you pretty precisely what the coordinates are, and I can even give you the volume. The volume is very small. So I mean, basically, you take any measure you want, and this is really minuscule volume. And so chances are you're going to have more like I think 2 on average, much closer to 2. But I mean, this would be a real nice digression. But maybe I'll just mention it really quickly. It is work of Berger, Erger, one of my former students, and Tonelli Quetti.
So it's really sensitive to the coefficients.
Excuse me?
Really sensitive to the coefficients.
Well, careful. If you fix the exponents, then you let the coefficients be random. So yeah, you're right. It is sensitive to coefficients, but what I mean is you average over the coefficients. Fix the exponents, average over the coefficients. What's the average number of real roots?
So I did F solve of this in Maple.
Yeah.
And 1 root.
Oh yeah. It's sensitive to coefficients. Yeah, it's very sensitive. So, but did you do try it algebraically?
Oh yeah, well, I have to read. It's done with the full screen.
See. See, it's still not trivial. It's not trivial. No, but it's a nerve. I mean, okay. In the worst case, I might have flipped the sign around or something, but it'll have 5. Okay.
And you took A equals B, alpha equals beta A or something.
Yeah, you can even take alpha equals beta. Yeah. So that's the thing. That's how we found it, because if you limit yourself to a line, then you have a greater chance of finding what's going on. So it took a while, but we did. So. There is some recent work, and actually there's some really beautiful bounds, and they're quite nice. All right, but I want to get to another motivation for the discriminant thing. So my point is that in high school we learned about discriminants, and tells us something about the number with real roots, sign of the discriminant, but the discriminant variety, set of coefficient values giving you a degenerate root, separates the coefficient space into regions where we have different numbers of roots, and there's even more. So here's another example of discriminants, and this one's going to be more important. So I want you to consider the following. Consider, I want to say this guy. Let's be really careful about this. I think we'll do alpha x. Hang on a second. Yeah. Plus beta y plus x to the fourth, or minus, maybe minus. Hang on a second. I want to be careful about this. This, yeah, it's minus x y to the fourth. Do that. So consider this guy. This guy. Okay? So this is my f of x1. Okay. What does the set of real zeros look like? So this is something that we all want to know. I mean, if you have a polynomial, somebody gives you a polynomial in many variables, how do you look at its real zero set? So Viro came up with this method, a very combinatorial method, for looking at real zero sets. And it's a very useful method, but it doesn't cover all possible cases. And so the reason I'm looking at this example is because it illustrates this example of exotic chambers again. So around the 80s, Rowe gave a method to classify real zero sets up to isotopy. Up to isotopy. Sometimes. There's all kinds of technicalities going on here. So the way his method worked roughly was to build a polyhedral complex which had the same isotopy type as your zero set in some sense. That's roughly what the idea was. And so the construction would be something like this. So the construction, roughly, would start from the sign mutant polytope and yield a piecewise linear curve. Okay, so what I mean by all this, well, here's what I mean. Okay, so you look at the exponents. 1 is the same thing as x to the 0, y to the 0, 0, 0. X is the same thing as x to the 1, y to the 0, so you have 1, 1, 0. And then y is the same thing as x to the 0, y to the 1. And then the next monomial term, x to the 4th, y to the 1. So you get this, 4, 1. By the way, Alexia, did you do the computation?
Yeah, well, I mean, for that?
Yeah, for that one, yeah.
So if I do Broken basis,
Yeah.
and if I do f solve of the, after I eliminate x,
Yeah.
then it gives 5.
Yes. Good, okay.
And I can solve for x.
Okay, good. Good.
Maybe there are more than 5.
It shows 5.
5 real ones. 5
Well, that's
I've
one
solved this.
projection.
No, I mean, there's a 0. It shows actually 6.
Yeah.
And it gives you 6. No, sorry.
Yeah, but the 6, well, the 6 is at the origin. There's a root of the
With
origin.
0, so you throw it out.
Yeah, throw it
You're
out,
only
yeah.
positive. not
Yeah,
Only positive.
positive. You suppose, yeah,
Yes.
5, yeah.
Yes.
I got 5.
Okay. So anyways, how does this construction go? I mean, without digressing too much. you look at the signs of the coefficients. So you have these, the monomials correspond to points, take the convex hull, and then the signs of the coefficients would be reduced here, minus, minus, plus, plus. And then somehow you'd introduce a triangulation. This triangulation, you generate this some other way. And then you start putting in midpoints for edges where you have alternating sign. I mean, you'd have some kind of construction for these midpoints. And see, and that's about it. And then you would connect these midpoints inside of the individual triangles. And you want to get something like 2 arcs or something. So without going into too much detail, Verreaux had this method which it works some of the time. And here's the interesting thing about discriminants. You can draw the alpha beta plane, and you can consider now the set of coefficient values, a set of alphas and betas, such that this curve has a singularity. And it looks very similar. It's going to be a little bit different looking. It's not different. It's going to be something like, I think this, something of this nature. Okay, so this curve, this is the Gauss alpha beta with f having a singular point. In other words, a place where the gradient vanishes. That's all it means. Okay. Hey, Mike, thanks for coming, Mike. Hope I'll catch you tomorrow. That's okay. I'll see you.
Diego.
Okay.
To Diego.
Yeah, I'll talk to you. Okay. Okay. So, what's my point? Well, my point is that Verreaux works in these large chambers. Verreaux works over here, and Verreaux works over here. And over here, he fails. Okay? So there's itty-bitty regions where Verreaux's method doesn't fail. And so basically, there are large regions in the coefficient space for combinatorics rules, and there's small regions in the coefficient space, these more exotic chambers, where things are crazier. And that's sort of where I'm really going today with this talk. So it turns out that I can give you, here's the upshot. So the upshot is this, that Verreaux's method generates curves, or generates at most no more than 2 kinetic components. So if you actually try to apply his method to these kinds of curves. But, concrete example, if you look at 1 minus x minus y plus 6/5 xy times x to the cube, something like this, x cubed plus y cubed. This guy has 3 kinetic components. Okay? So again,
by big chambers and small chambers just mean unbounded and or bounded?
I'll give you a precise definition in a moment. So this is a kind of a 2-hour talk or something, or 1 hour and plus or something?
Whatever.
Okay, whatever. Okay, so I'm not going to go too long. I'm not going to go too long. But what I'm trying to do is just give some general intuition. So 10 minutes ago, I was talking about 2 equations, 2 unknowns, and I was telling you that finding the maximal number of roots is kind of hard. But the extremal examples lie in a small chamber in the coefficient space. And over here, we have 1 polynomial, 2 variables, and this exotic topological behavior, that having 3 kinetic components, is rare. Winds up happening just here, this little part. Whereas everywhere else, the number of kinetic components is 2 or less. Okay? So now, it would be really nice if you could understand these chambers and try to get at them in a more computational way. And that's what I'm about to do. So I'm going to define rigorously what a discriminant variety is, and I will define rigorously what these small chambers are. But let me just give a break. I mean, I know people here, they've been waiting for a long time. Maybe this is an opportunity for people who need to leave or just take a break. So maybe just for 5 minutes. Okay.
A break?
Yeah, just a little small break, yeah.
Yeah, sure.
Yes, yes. So, yeah. Okay, okay. Yeah, so yeah, she was asking about Kovansky and Sebastianov. Yeah, so as far as I know, Sebastianov was a younger student who was very, very bright, and with Kovansky, he helped him get the key insight. I think it was some key example they needed to look at, and so this is where Fewnomial theory started.
Did you ever write a paper Did his name appear in any paper?
I think his name appeared in some papers, but he died young. I mean, I forgot the exact circumstances, but it was very tragic.
Oh, okay.
So he died pretty young. I think, below the age of 30, certainly.
Oh, wow.
Yeah. So, it was very tragic. But anyways, let me say something a little more rigorous about discriminants. So, just as a little example, more rigorously, I'll express misspelling rigorously, you can consider this. Those alpha beta such that 1 minus alpha x minus beta y plus x to the fourth y so the fourth equals 0, and then the partial of this with respect to x equals 0, and the partial of this with respect to y equals 0. You can do this, and by elimination theory, what you can do is get a polynomial whose vanishing is equivalent to this guy having a solution. And so you wind up getting a homogeneous polynomial. Actually, he's not homogeneous. He's going to be a polynomial in alpha beta. And the polynomial in alpha beta winds up being pretty big. And let me see if I can tell you how big it is. That's one of the reasons you want to have a different definition for these guys. So, where is he? Yes. So you actually can compute them in Maple, okay? So, I was hoping to write down a nice big coefficient, but this polynomial is a bit unwieldy. So this is unwieldy. So it's not going to kill you, but I mean, you can compute it in Maple. You can't write it in one line. It's going to take several lines, maybe a page. It's easy to build examples where you're going to get pages and pages and pages of polynomial. So a better approach is the following. Try parameterizing the discriminant variety. And this really, really makes your life a lot easier. And in fact, when you approach things this way, it gets rather interesting. So this goes back to work of Horn and Kapranov. Well, they didn't work together, but I think it was Jakob Horn around the 19th century and Misha Kapranov around 1990. He found a very, very nice parametric formula. So I'll try to write this in the right way. So here's a definition. Well, better. Let me say one more thing. Even better. Even better. Extend to exponential sums. So here's kind of a cute technical thing. Yes.
Maurice, I'm surprised that just for this case, two variables degree 4, discriminant can cause pages and pages of output?
No, not pages and pages. This one is a little bit painful, but it's not that bad. You can compute it in Maple. I mean,
right.
yeah, maybe
So
a paragraph.
Okay.
Yeah, it's not that bad. But what I mean is that you can easily make this more complicated. If you just up the degree a little bit, you can get pages and pages. If you want to put in 10 and 10, or 15 and 15, it'll get really unwieldy. It will. Give it a try.
So you're saying that the discriminant, it's still sparse. It's a
No, the polynomial is sparse, but I'm talking about the discriminant of this family of
That's
polynomials.
right. The discriminant of that is still, well,
you can say
be sparse, but bounded, of course, in the sparsity.
It's not going to be it's going to have a huge number of terms. It's going to have a huge number of
It
terms.
depends on the degree, you mean?
Depends on the degree, not just on the sparsity.
I see.
Yeah.
It spreads out, I guess.
Yes.
I see.
Yeah, actually, you can build even simpler examples. I mean, here's the thing. If you look at one polynomial, one variable, 3 terms, that actually has a very sparse discriminant. That's like a binomial. But if you look at one polynomial, 4 terms, already that blows up.
I see.
Okay, so discriminants of sparse polynomials are not sparse. Far from it. Far from it. Okay. Yeah, I should have given you a more dramatic example, but I mean, you can easily get examples where the coefficients have like 12 digits or like 100 digits. It's really easy to make big ones. All right. So you can actually extend this idea. I mean, here's where it gets interesting. You have, for polynomials, you have elimination theory, and you have commutative algebra, and you have all these tools. But what happens if you have something with real exponents? What do you do? I mean, can you apply elimination theory? Well, you can't anymore. And so that's where it really helps to parameterize discriminants. So now let me finally give you the definition. So here's the definition.
It is pages and pages.
It is, thank you.
After 10. Yeah, if I do 10, it's pages.
Yeah, there you go. Okay, you got it.
It's the pages.
So,
Wow. Well, the constants are huge, right?
Yeah, the constant.
Yeah.
That's the coefficient.
There you go.
The coefficients.
so see, I hired Alexei before I before my talk. Alexei's keeping me honest. So here's what you do. Let's let A be a matrix with real entries.
But before you go on,
Yeah.
what do you mean by parameterizing the discriminant?
Oh, because you'll see in a minute. You can describe an algebraic variety by a defining polynomial or by parameterizing it.
Oh,
So if it's a unirational variety, you can actually get an explicit parameterization of it in terms of rational functions or maybe radicals. If it's an arbitrary algebraic variety, maybe you can't parameterize it by algebraic functions or by radicals.
functions or whatever.
You need fancier functions. But it turns out discriminants can always be parameterized nicely. And not only that, discriminants of exponential sums can be parameterized nicely. That's where it's
By
really
analytic functions.
by analytic functions in a very compact way. One line. There's a one-line formula for the parameterization.
Okay.
That's what I'm getting at. So consider this guy. I'm going to consider a matrix. He's got real entries, and he's n by n plus k. Let's see. And there's going to be a technical assumption. This is with, okay, let's do this thing. Yeah, it's going to have columns. A1 through an plus k. Okay? Let A hat be this matrix. So it's going to be a matrix where I take these columns, I'll consider these guys columns, dot, this, A n plus k, that, okay. So this is going to be a matrix which is n plus 1 by n plus k. So I'll let this happen, so A hat. Of course, the A's are going to have columns A1 through n plus k. These guys are actually going to be the exponent vectors in my exponential sum, or these things that I take the dot product with. This A hat is lifted in one dimension higher. And assume the rank of A hat equals, I need n plus 1, I believe, yeah, n plus 1. Okay, that's a very mild assumption, which I'll say a little bit more about later. Let B be a matrix in here, and thanks to the rank assumption, it'll all work. It'll be a matrix in here, n plus k by k minus 1. Be any matrix whose columns form a basis. For the right null space. Of A hat. Okay? And I'm going to need a little more notation. I think I'm going to need some betas. I guess. I don't even need that. Finally, we define this. Finally. Let this guy C A B be defined to be a map going from the vector space, C n plus k, sorry, this is k minus 2, yeah. Cut this to R to the k minus 1, this be defined by this. CAB, lambda. Yes, so we'll handle this. So this is going to be projective coordinates. So if I want to write this out more explicitly, this would be something like lambda naught dot lambda k minus 1, something like this. Okay. So it's a total of k minus 2, k minus 1. Sorry. Total of k minus 1 coordinates here equals this. So the notation's a bit funny. It will be log of absolute value, E transpose, this guy, multiplied by D. Okay, so let's make sense of this. What am I doing? This guy here, this guy, when I take away the brackets, this guy consists of k minus 1 different coordinates. So this is actually a 1 by k minus 1 vector. Okay? This guy is a matrix. He's supposed to be a matrix of a certain size. He's supposed to be n plus k by k minus 1. So if I take the transpose, it is a k minus 1 by n plus k matrix. Okay? So when I multiply these guys together, I get 1 by n plus k. 1 by n plus k. In this matrix here, he is n plus k by k minus 1. So it all works out. So when I say log absolute value, I take log absolute value coordinate-wise of this vector. So I get a vector multiplied by that matrix. It's a vector. Okay, I get a row vector. In the end, I get a row vector, which is 1 by k minus 1. Okay? All right, strange-looking map. Strange-looking map. And the claim is that this actually parameterizes the discriminant in a really interesting way. That is the claim. Okay, so you call this guy gamma AB here. I'll do this, I'm going to take the closure AB. This guy takes P of k minus 2, like this guy, to R, this, that. This closure, a generalized discriminant contour. It's actually a reduced discriminant contour. A reduced discriminant contour. So sorry, it's a bit of a mouthful, but I'll give you a very, very specific example of this. So what is this getting at? Why should this matter? So I'll give you the theorem in a rough way, then I'll give you an example in a more rigorous way. So here's the theorem. So gamma AB is up to a linear isomorphism a section. I don't even do linear isomorphism. I'll just say a section. Is a section. Is a linear section of log absolute value of the discriminant variety. Okay, so we needed to look at the discriminant variety, or actually, sorry, I want to say this real part of the discriminant variety. Real part. Discriminant variety. So we wanted to study the number of kinetic components of a real zero set of a exponential sum. And I claimed that if you look in coefficient space, there's a discriminant variety. This discriminant variety is difficult to handle. So Alexei just did a computation already in the case of integer frequencies or polynomials. He got some wheel. But what did I just do here? I gave you a parameterization. Look, this is the parameterization. This is one line. One line. That's it. So Lexi said you get pages and pages for just mile degree. One line, parameterization.
So what is, give the example that you will.
Yeah, I'm going to give you the example.
In terms of this map, what is this map?
Yeah. So here's the thing. So let's go to our example. It's right here. Take A equal to this, 0, 0, 1, 0, 0, 1, 4, 1, 1, 4. This is actually the family of polynomials that I described a few minutes ago. If you do that, then B equals this, and the coordinates didn't even matter, but I'll just write it down anyways. I'll write down 3 coordinates. So I just threw this into MATLAB. You could even throw this into MATLAB, it's really easy. 0.8069, this. I'm not even going to bother with more points. So you see, the point is, here I have decimals. Okay, I'm no longer working with integers, I'm working just with floating point numbers. So that's the B that works. And if you go through this entire process, you get this curve. You get a curve which looks like this. Okay, really bad at drawing, but something like this. And then that and that. So you get some strange curve which looks a little bit like this. So it's in the end it's got 5 tentacles. Okay, that's what happens. And this actually turns out to be exactly the image of log absolute value of the discriminant. That's exactly it. And maybe this example isn't very impressive, but now if you throw in degree 55, or whatever you want, the curve will be equally easy, and the parameterization is going to be equally easy. And you get this, and you don't have to worry about massive polynomials. Not only that, but you can consider exponents like this. Suppose I have 4.2 and square root of 2. Okay? No longer polynomial. Parameterization still works. That's why I insisted on using floating point numbers here. All right, so I said it's a linear section. So actually what happens, the discriminant variety is sitting in higher dimensional space, but it turns out to have a very special structure. It turns out to be a subspace bundle over a base, and what you're doing with this parameterization is actually getting a linear section of the discriminant variety. You're getting the portion of the base that matters. Okay, so this is exactly what you want to look at. Okay. So, without getting too much more technical, this is the parameterization which is going to save our life and is going to allow us to prove theorems. Okay, so now we can begin to talk about.
So you're saying A could be real numbers?
Oh yeah, it could be real numbers. Yes. Thanks for coming, Victor. I hope to see you again. Yeah.
Don't you run into trouble with it's not finite anymore. The number of roots are not bounded anymore.
Oh no, you don't have any trouble at all. You in fact get a bounded number of connected components. That's what you're looking at is having singularities or not, and you get a bound on the number of connected components. So it's
because such polynomials, won't have a degree. It's another integer. So,
but it's an exponential sum. It's an exponential sum.
Exponential sum.
Yeah, and a byproduct of this is that exponential sums have a bounded number of real roots. Actually, you can go back to Kovansky. Like Kovansky would prove this for you, but with much worse bounds. But now here we have a more precise way of proving it. All right, so what I have so far is just the definition of how to parameterize the discriminant. I haven't told you what this has to do with root counting, so now I have to explain where the root counting comes in. Okay, so I don't want to erase my definition entirely here. I think I'll erase over here. Okay, okay, I did find this, I did that. Okay, I'll erase over here. All right, so now how do I get a bound out of this? I mean, she asked a very good question. So these exponential sums, they behave really strangely. I don't know anything about these guys. So I want to get to a more precise definition here. Yes?
Could you explain how you got the matrix from the...
Oh, that I literally just did by Gaussian elimination. Or I asked MATLAB to give me a basis for the null space.
No, A.